Hello everyone, welcome to the Computer Network lecture series. In this particular session, we'll study about the analog transmission. The very first topic is digital to analog conversion. So what is this actually? So it is the process of changing one of the characteristics of the analog signal based on the information in the digital signal. So we have a digital signal or digital data. We need to convert it into analog signal based on some characteristics. Like here, suppose we have this the digital data 1010 in any format. Then the sender uses a modulator, so it changes this digital data into analog data, and it sends this data through the link. And at the receiving end, the receiver uses a demodulator, and it recovers the digital data from the analog data. So the modulator, it converts the digital data to analog signal, and demodulator, it converts the analog data to digital signal. Now there are various types of conversion. So these are the conversions. The first one is amplitude shift keying, ASK. Second is frequency shift keying, FSK. Third is phase shift keying, PSK. And we combine the ASK and PSK to get quadrature amplitude modulation, that is QAM. So first of all, let us see what is the meaning of amplitude shift keying. So in this case, the amplitude of a carrier, so we have something called as a carrier signal. So this in this case, the amplitude of the carrier is changed with respect to the whatever input data, input digital signal we have, and the frequency and phase, they do not change. So let us see with an example. So here we have the digital data is 101001. So we have used our dashed lines to discriminate with the different bits. So for sending 1, we have this signal. So this analog signal is sent. For 0, we are sending the amplitude at 0. For 1, this is the signal which we are sending. It is having some amplitude. And for every 1, we have the constant amplitude. Okay. And for 0, we have 0 amplitude. Again 0 amplitude. And again we have this 1. So this is how we convert this ASK, amplitude shift keying. Then next is frequency shift keying. So in this case, frequency of the carrier is changed with respect to the digital data, and amplitude and phase, they remain constant. So let us see how it works in the same data 101001. So for sending 1, we send this particular analog signal. For 1, we send this one. So if we observe these two signals, for 1 the frequency is less, and for 0 frequency is more. Okay, so these are the, as we can see, amplitude and phase, they are not changing. The amplitude is fixed, the height, that is the amplitude, is fixed, and the phase is also 0. So this is 1, 0, then again 0, then 1. So this is how frequency shift keying works. Now next is before starting with PSK, phase shift keying, we understand the concept of phase of the signals. So this is a particular input signal, and we have another one. So there is phase shift of 0. These are two signals starting with same phase. Now suppose if we move this signal a little bit further, so in this case there is a phase shift of 90 degree. So this signal, the second one, is out of phase with 90 degree. So this is actually, if we consider this entire wave, it consists of 180, it consists of 360 degree. So half of the wave is 180, and still half of that half wave becomes 90. So this wave, it starts from this. So there is a phase. If we draw a single line from here, we see this is actually 90 degree. Then this one, okay, in this case the two signals, they are differing by a phase of 180 degree. So this entire half wave, okay, this is a 180 degree wave, and this is starting after 180 degree. So this is the phase shift is 180 degree. So keeping this concepts of phase angle in mind, we continue with the phase shift keying. So in case of phase shift keying, the phase of the carrier signal is changed with respect to the digital data, while the amplitude and frequency, they do not change. So here again we take the same data 101001. So here for 1, the phase is 0. For 0, the phase is 180. As you can see, this particular wave is reverse actually. So we have this phase is of 180 degrees. So the green wave is having phase of 0, and the blue wave is having the phase of 180 degree. So this is what we get. So amplitude and frequency are not changing, only phase is changing. For every 0 we have this 180 phase signal, and for every 1 we have 0 phase signal. Now next is quadrature phase shift keying or quadrature modulation. So here we represent like for 0 0 we use this 0 phase, for 0 1 we use this particular phase of 90 degree, for 1 0 we use a phase of 180 degree, and for 1 1 we use a phase of 270 degrees. So these are the various signals for the various bits. So the thing is, here we are having 2 bits, we represent 2 bits, okay, for a, so one signal represents 2 digital bits, okay. So let us see further. So what is quadrature phase shift keying? So in this case, different phases of the carrier, they represent the bits, while amplitude and frequency they remain constant. So here we have this. So as we saw the previous representation of 4 different signals, so we have this, okay, the different signals we can see here, okay. So this is how we represent. So the advantage in this case is that one signal, it represents 2 bits rather than 1 bits. So that is the advantage. Now let us go to the next topic, that is the constellation diagram. So constellation diagram, they illustrate how different modulation schemes we can use amplitude and phase to convey the information efficiently. So we can use different amplitudes, different phases can be used to represent the different phase, the different signals. So let us see what are these constellation diagrams are. So they provide a clear visual of how signal elements differ in case of amplitude and phase. So they are particularly useful when we are using 2 carriers, that is one is in phase and other is called as the quadrature. So each signal element type is represented as a dot on the constellation diagram. Let us see this diagram. So the position of each dot, it specifies the amplitude and the phase of that particular signal element. So this is the constellation diagram we are talking about. So on the x-axis we have the in phase carrier, on the y-axis we have the quadrature carrier. So this is one signal element which is represented by this particular dot or circle. So this is the amplitude, okay, and this part, okay, this is having 2 components. One is the y component, so y component is the amplitude of the q component, and the x is the amplitude of the I, that is the in phase component, and here it gives the phase. So in this case we can say if we measure this angle, it becomes 45 degrees. So this is the use. Now in case of quadrature amplitude modulation, it is combination of ASK and PSK. So here we have 4 different signal elements, okay. So here this, the one in violet, it represents one amplitude and angle is 45 degree with respect to the positive x-axis. Then the orange circle, it is having the same amplitude, but the angle, if we measure with respect to the x-axis, it is I think it may be like 90 plus 20, it is 135 around. So this is what we are having, different angles here we are having. So this is how we represent the quadrature amplitude modulation. So this particular represents 0 0, this represents 0 1, this is 1 0, this is 1 1. So this is there are only 4 dots here, or 4 signal elements. We can even actually have more signals, like we can have, after this we can have one more amplitude here, okay. So it becomes like 16 can also be there. Now let us go to the next topic, that is analog to analog conversion. So what is actually analog to analog conversion? So this is also called as modulation actually, okay. So this modulation is necessary due to the following. Why do we need to convert an analog signal to analog? Of course analog to digital is understood, digital to analog is understood, but why analog to analog conversion? So we must understand what are the reasons. So the first is the efficient use of spectrum using multiplexing. So if we have a large bandwidth, then just sending one signal, one analog signal, will be wasting the bandwidth. So what we do is we divide that particular bandwidth into number of different signal elements. So this is done by using the modulation. So different carrier frequencies are given in that particular bandwidth, so we can make an efficient use, okay, that we'll see afterwards. Then it also reduces the size of the antenna. Now generally when we want to transfer the signals, they are actually voice signals, Okay, these voice signals, the frequency is from 20 hertz to 20 kilohertz. So voice data, which we can actually hear, which what we talk, that is that actually frequency is very very low. And to design antenna for that, the size of the antenna would be around 1000 kilometer, 2000 kilometer. It is not possible to make such a big antennas. So what we do is we actually convert this signal, low frequency signal, to very high frequency signal, so that because of this the size of the antenna also becomes very much small. As we can see in our mobile phone, there is an antenna, but the size is very very small. It is we can't even see the antenna, it is inside the chip. Then we have improved signal propagation. So with high frequency, the quality of signal also gets improved, and it also avoids interference. So because we are using different carrier frequencies, there is no chance of interference. Now this modulation is of various types. So here we can see there are three types of modulation. One is called as amplitude modulation, AM. Second is frequency modulation, FM. Third is phase modulation, PM. Now let us see first is the amplitude modulation. So in case of AM, that is amplitude modulation, the amplitude of the carrier wave, it changes according to the amplitude of the signal or the modulating wave. So we want to send the signal. This signal or the information is very low frequency wave. So we convert, we actually mix this signal with one more signal, that is a carrier wave, and it is a very high frequency wave. So in this case, the amplitude of the carrier is changing, okay, and frequency and phase, they do not change. So this is the carrier wave, and this is the signal wave. The signal wave is the information which we want to send, and it is having a very low frequency, and carrier is having high frequency. So we mix this two using an AM circuit, and this is what we get. As we can see, the amplitude is changing. So we are actually sending the carrier wave, but the amplitude is following the signal wave. The envelope, we can see the upper and the lower part of this particular wave, they are resembling, the amplitude is changing according to the signal wave, as we can see in this particular diagram. Then this we have something called as AM radios, broadcasting radios. So this AM allocation, so we have various we can say rules actually. So this AM radio station, it needs a 10 kilohertz bandwidth, because audio signals, they require a bandwidth of 5 kilohertz. So this much is actually allocated. So FCC organization, it allocates 10 kilohertz bandwidth for each AM station, and this AM radio station, they are allocated frequencies from 530 kilohertz to 1700 kilohertz. So this is universal throughout the world, that every AM station is allocated frequencies between this particular range, 530 kilohertz to 1700 kilohertz. So each station's carrier frequency, it is 10 kilohertz apart, so that there is no interference. So as we can see, this is the distribution of frequencies from 530 kilohertz to 1700 kilohertz. So every station is allocated a carrier frequency, and they get a bandwidth of 10 kilohertz. Okay, so this is what we have in case of AM radio. Now next is FM, that is the frequency modulation. So in frequency modulation, the frequency of the carrier is changed according to the amplitude of the signal wave or the modulating wave, that is the information. The amplitude and phase, they do not change. So this is the carrier wave again, and this is a signal wave. Now in this case, as we can see, the amplitude is not varying, but the frequency is varying. So in those regions where the signal wave is having high amplitude, we can see there is a this waves actually, they are compressed, and where the signal wave is having negative, it is going down, negative amplitude, so there is a rarefactions. So they actually spread the FM wave. So this is the below diagram is the FM wave. Okay, now in case of frequency modulation, we have the FM radio. So FM radio station, they have a bandwidth of 200 kilohertz. Every FM radio, it has a bandwidth of 200 kilohertz. It is, we can say, 20 times more than AM. Therefore FM signals, FM radio, they have a good quality. So FCC, it assigns the frequency for FM radios from 88 megahertz to 108 megahertz. So each station is separated by a distance of 10 kilohertz actually, so that there is no interference. So this is what we have. So it starts from 88 megahertz and goes up to 108 megahertz, and every station gets a bandwidth of 200 kilohertz. So more, it is 20 times more than AM. Therefore the quality of FM is much better than AM radios. The last one is the phase modulation. So in phase modulation, the phase of the carrier is changed with respect to the amplitude of the signal or the modulating wave, while this we can say the amplitude of the carrier does not change. So this is the carrier wave, this is the signal wave, and here what we have, this is the PM wave. Okay, this is how we get the PM wave. Okay, this is the PM wave. So phase is changing according to the amplitude of the signal wave. So that's all for this particular session. Thanks for watching. Do join for the next video.